Hey everybody, and welcome to MAT 221. This is a quick review of sections 1.1 and 1.2 in your Stewart textbook, which is on representing functions and catalogs of essential functions that we learned in pre-calculus. This is review material, so I'm going to go through it relatively quickly as we move through, just as a quick review to get your brain up and going, thinking what of things you learned in pre-calculus. As in all things in mathematics, especially at the college level, we're going to look at things using the rule of 4. This is called the Harvard method of mathematics, and we're going to look at things in 4 ways. We're going to look at things numerically, graphically, analytically, or symbolically, and verbally. This is a standard way of teaching mathematics. We want to look at things in these 4 ways. Especially in today's society, we want to look at things numerically because data and tables. We always like to take that data and establish a graph. Then from there, we establish what's called regression equations and formulas and doing some algebra or analytically or symbolically. And then lastly, we want to be able to make sure we can interpret our results in an intelligible, collegiate, smart form so that we can understand what these numbers mean. So as always in math, we're going to start off with what is a function? A function can be, by formal definition, a function is a rule that takes a certain numbers as inputs and assigns each to a definite output number. A function is a mathematical machine of sorts. It actually is like a mathematical machine. It takes whatever we give it in input, we put it into that machine. That's called the function machine. In this case, we call the function machine f. That machine will change it in some way and give us an output. The output obviously depends on what we put in and depends on what the machine did to it. The input values are called the domain or the independent variable. The function itself is the machine that does the work to the input that we give the machine. That's the name of the machine. Most common in mathematics we use F, G, or H, but they could be any name could be there. And the output that comes out of this mathematical machine called a function is called the range, and it's called the dependent variable, which makes perfect sense because it depends on what we put in. The result depends on what the input was. So here, remember, the function is simply a machine that assigns a rule. What goes into this is called the input, the domain, or the independent variable. What comes out is called the range, so it's definitely like a machine. So if I called this machine take everything I give you and square it and add 2. That's what this machine does to whatever is input. So if I input 5, it will square that input and then add 2 to get a result of 27. So in this case, we get a numerical result. Remember often, though, that a function can be not always given as an analytical function. It can actually be given, or an analytical symbolic form, it can be given as a set of data. So in this case, we have a set of data. What does it represent? Does it represent a function? How do we know? Why or why not? And what is the domain? So let's look at this. My inputs here are the years. It looks like the years since 1900 to 2000. So my domain is from the year 1900 to the year 2000, incrementing by tens. My output is the population of something. Doesn't tell me what. Maybe population of the world or whatever, in millions of people. And it looks like my range here ranges from a low of 1650 to a high of 6080. Looks like it's increasing throughout. Now, how do I know whether a set of data represents a function? Well, what I look for is, for every input, do I have a unique output? And I notice that I do. For each input, I have that same unique output. So in this case, I do have a function. Now, what about this? This is a graphical representation. Is this a function? What about this graph above? Is this a function? What is its domain and range? Well, I can still figure out its domain and range, whether or not it's a function or not. It looks as though this output, which is this blue curve here, the input values are all values. Remember, the input values here starts at an input value of -2, and then I get an input value from that point on. So my input value or my domain value is from -2 to infinity. And it looks like my output value looks like these, if I'm implying that these go on forever with arrows, looks like this might go on forever and this might go on forever. So if I look here in my range values would be from -infinity to infinity. Now, does this graph symbolically or graphically show me a function? And the answer is no. And the reason why we know this is we know that a function must pass the vertical line test. So notice I could still find the domain and range, which is the input and the output of the function, the input values and the output values of the function, what x values go in or what input values go in, what output values come out. But this is actually not a function. This is a relation. So it does not represent a function because it fails the vertical line test. So what about algebraically defined functions? Something like this. Again, notice I'm using the rule of 4. I started with data and tables, then I went to a graph. Now I'm going to algebraic or analytical definitions of function. Is this a function, f of x equals x squared? Well, yes, it is a function. Its domain, anything can go in. And we know that from our library of functions from pre-calc that this is a quadratic function. It looks like a parabola shape going upward. And the domain is any x can come in. I could put any x in there. Negatives, positive, doesn't matter. And then I just square it. But because I'm squaring it, the only thing that comes out are positive values or possibly 0, because if I put in 0, so if I looked at this, I said, okay, my domain is all reals. Again, in bounded notation from -infinity to infinity. And my range is from 0, including 0, to infinity. Remember, the bracket includes that value and is saying that there's a definite endpoint to the range. In other words, the last range value or the first range value is 0. And then up to infinity, and there is no it continues on, so there's no definite endpoint there. So the bracket indicates an endpoint included in the domain or range. The parentheses indicates no inclusion or no end to that particular value. What about this function, f of x equals 1 over x? Is this a function? It is. I can again put in almost everything value here. It is defined in function notation, except I cannot put in 0 into a denominator because we know in mathematics 0 is not defined in the denominator. So in this particular case, everything that goes in can be anything except for 0. So how do we do this in bounded notation or interval notation? We say everything from -infinity up to 0, but don't include it, and then start again at 0, but don't include it up to infinity. The same is true for the range in this case. Everything will come out of this function with the exception of 0. Again, a graph of this function would also help us with this. Here's f of x equals the square root of 4 minus x. Can every x go in here? Well, we know in mathematics a 0 in the denominator and a negative underneath a square root or an even root is not allowed. So anything that would make a negative value here would not be included in this domain. It would be not included in what is okay for this mathematical machine. So we'd say, okay, what is included? Well, I can put in almost every negative number because minus a negative would become a positive value. So that would include all the negative values. I can put 0 in there because 4 minus 0 is still 4, which is a positive value. And I can also put 4 in there. If I put in 4, I get 4 minus 0, which is 0. Excuse me, 4 minus 4, which is 0. And the square root of 0 is still 0. But anything bigger than 4, 4.1, 4.001, anything bigger than 4 is not allowed because then the radical, the square root, would have a negative value, which would give me imaginary numbers, which is not in the real number system. So its real domain is all numbers from -infinity to 4. Obviously, infinity includes the notice is that we don't have an endpoint, but then we'd have an endpoint here of 4. And then we'd say, okay, what range values come out? Well, we know that the only thing that can come out are positive numbers because we always have to have a positive number under here. So my range is from 0 to infinity. 0 is my first output value if I put in 4. and then any other number I put in will give me a positive output. So again, remember my range is my output values. Now what about this function? This function is saying, what about if I just say the positive square root of 4 minus x squared? What does that look like? Well, in this particular case, everything can go in here except for values that will make this, again, this radical negative. So I can't put in anything bigger than 2, but I also can't put anything lower than negative 2, because if I put in negative 3 and square it, I would get 4 minus 9, which would be a negative number, or even negative 2.1. That still would give me a negative number underneath that radical. So my domain is from negative 2 to 2, and my range, what comes out here, is only from 0 to 2. Now if we look at this, by the way, if we actually graph this, this is actually a semicircle. This is a semicircle, a circle of radius 2. If I said y equals radical 4 minus x squared and squared both sides, I would get y squared equals 4 minus x squared, or x squared plus y squared equals 4. Remember, that would be a semicircle, the upper part of the circle with a radius of 2 sitting at the origin. All right, lastly, let's look about functions in written form. When I turn on the hot water faucet, the temperature T of the water depends on how long the water has been running. Draw a rough graph of what this function might look like. All right, let's look at this function. We know that once I start here, I'm starting, my water temperature can go up to a certain amount, right? Because our hot water heater can only heat to a certain temperature. And then after a while, hot water will run out and the water will get down back to regular room temperature once again. So this would be a function. Piecewise functions. Piecewise functions are functions that are defined in pieces. For instance, this function looks like y equals negative x in the domain less than 0. So from negative infinity to 0, this function looks like the function y equals negative x. And then this function looks like the parabola y equals x squared from 0 to 1. And then from after 1, this function looks like the constant function 1. So this is called a piecewise function. It's a function that is defined in pieces of its domain. So in this domain, it looks like this function. In this domain, it looks like this function. And in this domain, it looks like this function. These are called piecewise functions. The most famous of all the piecewise functions is the absolute value function. The absolute value function is actually defined as a piecewise function. In this lower domain, less than 0, it looks like negative x. And in the positive domain, it looks like positive x, and this is known as the absolute value function. Again, quick review of even and odd functions. An even function is a function such that if I get f of x, f of negative x will be the same as f of positive x. An odd function, f of negative x will be the negative value or the opposite sign of f of the positive input value for every x in its domain. Even functions are said to be symmetric about the y-axis, and you could close this as if you're closing the book, as if the binding of a book were the y-axis, and you could close the book over there and match both sides. These are called even functions. They have symmetry about the y-axis. And then odd functions have symmetry, point symmetry around the origin. So if you pick a point on the curve and then go straight to the origin, and then go straight the same distance on the other side of the origin, you should have a matching point. So if I go here, go straight to the origin, I should have its matching point somewhere on the other side. So we say that odd functions have symmetry about the origin. A function is increasing if the values of f of x increase as we move to left and right. In other words, it climbs as we move from left to right. A function is considered a decreasing function if the function decreases as the input increases. Its rate of change is negative. Notice an increasing function has a rate of change that is positive. And monotonic functions are functions that only increase or only decrease.